Hello, everyone. I'm Diptak Bhattacharya. I'm a grad student in the MME Department of Colorado School of Mines. The topic of my presentation today is microstructural influence on liquid metal embrittlement sensitivity of zinc-coated advanced high-strength steels. I would like to first thank my advisors and my multiple industrial mentors for their continuous support and enthusiasm in this project. Now, this problem of liquid metal embrittlement has surfaced very recently, but it's of huge concern to the automotive industry. So let me first tell you what is LME. So if you have a zinc-coated steel, the zinc coating typically has a lower melting temperature than that of the steel. When you heat the steel to a temperature above the zinc melting temperature, so there is liquid zinc on top of your solid steel. Now in that condition, if you're applying a tensile stress, then liquid zinc from the coating starts penetrating into the steel via the grain boundaries of the steel, weakening the steel, resulting in the formation of cracks in the steel. And this problem is typically encountered during resistance spot welding. So the picture to the left, that's a spot weld LME crack. And when we analyze these cracks, we find this is the SEM image of the crack. This is the corresponding zinc EDS map, which tells us that the zinc from the coating has penetrated into the steel. So that's an LME crack. Now, several researchers in the past has tried to analyze different steels to try and find out which steel is more LME sensitive compared to another. So this is the conventional strength ductility diagram, or the banana diagram, which is a famous diagram in the steel and the automotive industry. And here are the various researches that has been done on the different types of steels available in the market today. And the result is very clear. The advanced high strength steels having a strength level of more than 1 GPa are clearly more LME sensitive compared to the other steels. Now we clearly don't know why. And some of these advanced high-strength steels, they were developed right over here in Colorado School of Mines. So we really need to know what is inducing this high LME sensitivity of advanced high-strength steels. But we do not know why, because of the fact that different steels in this list has different microstructure, they have different composition, and both microstructure and composition can affect the zinc LME susceptibility of a steel. So we need to decouple the influence of microstructure and composition to understand what is contributing to the LME sensitivity of advanced high-strength steels. So we asked ourselves this question: does the microstructure specifically affect the zinc LME sensitivity of advanced high-strength steel? So how do we get an answer? So we use a steel of a fixed composition. We develop different microstructures at the fixed composition because we cannot afford to change the composition, because composition is an additional variable for LME. After we develop different microstructures at a fixed composition, we test the LME sensitivity of these different microstructures. So I'll drive you through this process of how we did this. So we started with an experimental cold rolled alloy having an AHSS composition. The as received microstructure was cold rolled ferrite perlite. We developed 4 different heat treatment cycles to develop 4 different microstructures. So this is the martensitic cycle, the quench and partition, or the QNP cycle, the trip Benedict ferrite, or the TBF cycle, and here is the dual phase cycle, or the DP cycle. Please note that the martensitic QNP and TBF steels were completely austenitized before the martensite QNP or TBF microstructures were produced. In contrast, the DP steel was generated through intercritical annealing. So that's an important thing that we have to keep in mind. We'll be coming back to it later on. Here are the 4 different microstructures corresponding to the cycles that I showed in the previous slide. This is the martensitic microstructure, which is martensite, the quench and partition microstructure, which is martensite and regent austenite, the TBF microstructure, which has martensite and bainite, and the dual phase microstructure, which is ferrite and martensite. So it will be very interesting to note the LME sensitivity of these 4 microstructures at a fixed composition. Now, to know the LME sensitivity, we have to first apply the zinc coating. So we applied the zinc coating via electrogalvanizing. So we electrodeposited zinc on the surface of the steel, and then we did hot tensile testing at different temperatures above the zinc melting temperature. Now over here in this presentation, I'm showing the results for hot tensile test at 500 degrees C, which is not very far above the zinc melting temperature of 420 degrees C. And the next slide has the big reveal. So zinc LME susceptibility as a function of AHSS microstructure, we find that the martensitic microstructure, QNP microstructure, TBF microstructure all formed large LME cracks In contrast, the dual phase microstructure did not form LME crack. There was only one small LME crack compared to the large cracks in the martensitic QNP and TBF steel. It's very interesting because the martensitic QNP and TBF steels had very different starting microstructures, but yet they formed these LME cracks, which means neither these presence of reagent austenite in the QNP steel or the presence of bainite in the TBF steel affected the LME sensitivity of the QNP or the TBF steels. In contrast, the dual phase steel with a microstructure of ferrite and martensite does not form LME cracks. So it is very important an analysis and a very important thing to note. Now we need to explain this observation though. So in order to explain this observation, we have to find out what boundaries cracked in the martensitic or the QNP steel. So we analyze the tip of these LME cracks in the martensitic and the QNP steel, and let me show you the results of that. So here is the EBSD IPF, or the inverse pole figure from the LME crack in the martensitic microstructure. The EBSD IPF tells you that there are tons of boundaries in the martensitic microstructure. There are block boundaries, lat boundaries, packet boundaries, there are prior austenite boundaries. So what is the preferred path for LME crack, or what path did the LME crack take to crack? So we use the EBSD IPF to reconstruct the prior austenitic microstructure, the austenite that was present before the martensitic microstructure was formed. So here is the EBSD IPF of the reconstructed prior austenitic microstructure, and what do we see? So here is the LME crack over here corresponding to this, and what we find is that the austenite orientations, or the prior austenite orientations on the two sides of the crack are different, which means that the LME crack in the martensitic microstructure was formed via prior austenite boundaries, not lat boundaries, not block boundaries, not packet boundaries, nothing. Prior austenite boundaries were responsible for forming LME cracks. Now, what about the QNP microstructure, which is different from the martensitic microstructure? So here is the EBSD IPF of the crack in the QNP microstructure. The phase map says that there was not only martensite, which is the green part, there is also these red phases. The red is the retent austenite in the QNP microstructure. We carefully looked into the orientation of the retent austenite on two sides of the crack. So here is the orientation map of the retent austenite, and what we find that the retent austenite on the two sides of the crack have different orientations. Now, what does that mean? It means that the crack in the QNP microstructure again followed prior austenite boundaries. So the prior austenite boundaries were responsible for LME cracking in the martensitic QNP and also in the TBFC, which I'm not showing over here, but we have also analyzed all these microstructures cracked because of the presence of prior austenite boundaries. Now, what happened with the DP microstructure? So here is a hypothesis for why the LME was suppressed in the DP microstructure. I call it a hypothesis because I really do not know why the prior austenite boundaries are prone to cracking. So here is the QNP microstructure. Here is the DP microstructure. The QNP microstructure has martensite and retent austenite. The DP microstructure, which did not crack, had martensite and ferrite. Now, in order to understand why these two microstructures have different LME behavior, we have to first understand how these microstructures were produced. The QNP microstructure was formed by full austenitization, whereas the DP microstructure was formed by intercritical annealing. So the high temperature microstructures before the QNP or the DP structure was formed was fully austenite in the case of the QNP steel. It was ferrite and austenite in the case of the DP steel. Now, upon cooling, the martensite formed inside of the austenite grains in both the steels. So here is the martensite in the QNP steel, here is the martensite inside the DP steel. So the red is the prior austenite boundary, and what do we see? The prior austenite boundaries are well connected and have a larger area fraction in the QNP steel. In contrast, the DP steel, the prior austenite grain boundaries have a smaller area fraction, and on top of that, the boundaries are not well connected. Now, these prior austenite boundaries are responsible for the LME crack, and it is present as a continuous network in the QNP specimen, which helps the LME crack to form. And in case of the DP steel, they are present in a clustered format here and there, and therefore they do not allow the LME cracks to form. And so our conclusion from this study is that the starting microstructure can definitely influence LME sensitivity of steels. The dual phase microstructure has suppressed LME behavior at high temperatures. We clearly saw the dual phase microstructure did not crack sufficiently enough compared to the other steels. The prior austenite grain boundaries were responsible for the similar extent of cracking of the martensitic TBF and QNP specimens. and perhaps the less area of the prior austenite boundaries suppress the LME cracking of the TP steels. So that is my presentation. I really thank you for your time. And also, if you have any question, then please ask me at this email address. Thank you very much.